A moon of Saturn was hit so hard that the impactor should have shattered it completely, and the crater that survived tells a story about ice physics and planetary resilience that scientists are still working through today. The crater is called Odysseus, the moon is Tethys, and the numbers behind both of them are genuinely difficult to process without stopping to reconsider what you thought you knew about how solid objects survive catastrophic impacts. Tethys is a mid-sized moon of Saturn with a diameter of approximately 1,062 kilometers, comparable in size to the distance across Texas. It is composed almost entirely of water ice, with a density so close to that of pure water ice, about 0.97 grams per cubic centimeter, that it contains almost no rocky material at all. For a moon this size, that composition is unusual and makes Tethys one of the least dense bodies of significant size in the solar system. Odysseus crater sits in Tethys's western hemisphere. Its diameter is approximately 450 kilometers, meaning the crater is about 42% as wide as the entire moon it sits on. To put that in terrestrial context, if you scaled Odysseus to Earth, it would be a crater wider than the continental United States from coast to coast. The impactor that created it was estimated to be tens of kilometers across, large enough that the energy released during the collision was comparable to a significant fraction of Tethys's own gravitational binding energy, the energy that holds the moon together against being torn apart. The fact that Tethys exists at all is the surprising part. An impact this proportionally large on a rocky body would very likely have shattered it. But Tethys is ice, and ice, under the right conditions, particularly at low enough temperatures and over short enough timescales, can behave more like a fluid than a solid. At the moment of a catastrophic impact, the energy is deposited so rapidly and the pressures are so extreme that even a frozen water ice moon can deform and flow rather than simply fracturing into fragments. The current appearance of Odysseus supports this interpretation. The crater has an extremely flat floor. In a fresh impact crater on a rocky body, you would expect a deep bowl shape. On Tethys, the enormous crater has relaxed. The ice has slowly flowed under its own weight and internal heat over millions or billions of years, filling in the depression and producing a shallow, flat-floored basin. This process is called viscous relaxation, and it requires that the ice retain enough warmth and plasticity over geological timescales to gradually deform under gravity. The flatness of Odysseus is evidence not just of the impact, but of the subsequent geological history of Tethys's ice. In the center of Odysseus sits a central peak complex, a raised area formed during the impact rebound, where the surface bounced back upward after the initial compression. This is a common feature in large craters, and its preservation, even in a somewhat degraded form, tells scientists about the energy of the original impact and the mechanical response of the ice at the moment of collision. Tethys also carries a second extraordinary feature that is almost certainly connected to its violent impact history: Ithaca Chasma. This is a vast system of troughs and valleys that stretches approximately 2,000 kilometers across Tethys's surface, nearly 3/4 of the moon's circumference, reaching up to 100 kilometers wide and 3 to 5 kilometers deep. The leading hypothesis connects Ithaca Chasma to the same impact event that formed Odysseus, or to an earlier period when Tethys's interior ocean froze and expanded, cracking the crust. The geometric relationship between the canyon and the crater has been noted, though the exact causal connection remains under investigation. What Cassini's flybys of Tethys revealed is a world that carries its trauma on its surface. The crater is a record of a collision that should have ended the moon. The flat floor is a record of the ice slowly healing. The canyon may be a record of the rupture that nearly split it open. Tethys survived. It carries the evidence of why survival was not guaranteed. Follow for more on the most violent geological histories in the solar system. And tell me, knowing that Tethys survived an impact energetic enough to threaten its entire structure, because it is made of ice rather than rock, does that change how you think about which materials make a body more resilient in space?